What we're going to do then is we're going to look at and use these terms that we've brought up here at the end of class the other day and use them to apply to different properties of gases. And so they are directly proportional and inversely proportional. And then we are also going to look at these as they pertain to the pressure of a gas, which we're going to label with the letter P, the volume, which we're going to label with the letter V, and the temperature, which we're going to label with the letter T. And by the way, when we work with temperatures as they pertain to gas laws, these must be absolute temperatures. An absolute is a term from mathematics. If we talk about the absolute value of a number, that means we want to look for its positive value. So which temperature scale has only positive values? Kelvins, exactly. So the temperatures with the gas laws must be in units of kelvins. And that's because we can't have any negative temperature values when we work with the gas laws. Also, you're going to see these labels in your text as well as how I write them. Sometimes you'll see subscripts with the letter I, sometimes with subscripts of 1. I like to use the numbers. I think your author uses numbers as well. But if you see a subscript of I or a subscript of 1, this stands for initial conditions. And a subscript of F or a subscript of 2 stands for final conditions. Initial conditions and final conditions. So the first one we're going to look at, and this is going to be the first one on the Socrative app, there's a series of at least 3 questions coming up on the Socrative app that we're going to look at. And the first one relates pressure and volume. So I have a syringe here. What I'm going to do is I'm going to seal up the syringe by putting my finger on the bottom. And now I'm going to press down on the plunger. Notice what happens to the volume. I'm going to increase the pressure. Notice what happens to the volume. If I let go of the plunger, that means I'm decreasing the pressure. Watch what happens to the volume. So again, I increase the pressure. Watch what happens to the volume. I decrease the pressure. Watch what happens to the volume. Increase pressure, decrease pressure. Increase pressure, decrease pressure. What is the relationship between the pressure and volume of a gas? Are they directly proportional or are they inversely proportional? 3, 2, 1. And these are definitely in inverse proportion. And that's because as I increase the pressure, what's happening to the volume of the gas? Decrease. It's getting smaller. And as I decrease the pressure, what's happening to the volume? It's getting bigger. So again, pressure and volume are inversely proportional to each other. So if I were to write this, we'd say that P and V are inversely proportional. And this, of course, is assuming that we maintained a constant temperature, which we say is constant T. And this has been known for many years as Boyles Law, though I don't refer to it as that. Your text will mention it once or twice. It's named in honor of Robert Boyle, who described this back in the late 1600s. And the way that we write an equation that relates pressure and volume is like this. P1V1 is equal to P2V2. And this is how we write in inverse proportion between 2 variables. So our next one here I'm going to take a balloon I'm going to blow it up, and now we're going to change its temperature. And we're going to change the temperature using something really cold. And this is for some demos I'm going to be doing later on here today. This is some liquid nitrogen. And we'll pour the liquid nitrogen over the balloon. Now notice what's happening to the balloon itself. Shrinking in size, so now we'll put it in here. Now we're letting it warm back up. Notice what's happening to its size as it warms back up. Pour liquid nitrogen over it again to cool it down. And we pick it up. We let it warm back up. So the next question on the Socrative app is, and you can talk with a neighbor, is the relationship between pressure and temperature, is this directly proportional or is it inversely proportional? Think about what you've just observed. 3, 2, 1. And this is a direct proportion. Because, of course, when we cooled it down, what happened to the volume?
It went down.
It got smaller. When we warmed it up, what happened to the volume?
It increased.
Got bigger. This one's easy. Okay, direct proportions should be really easy. If they go in the same direction, it's a direct proportion. So, we then say that volume and temperature are directly proportional. And this is assuming constant pressure. And this here is known as Charles' Law, a French name, Charles' Law. And the way that we write a direct proportion is like this. V1 over T1 is equal to V2 over T2. And the next one we're going to do is between pressure and temperature. And so for this one now, I have a device that will help us out with this. This is a device that helps us maintain a constant volume. Maintains a constant volume because its size does not change. You see that there's a pressure gauge on here, and I'm going to lower this into the liquid nitrogen. And remember, liquid nitrogen is this hot or cold? Cold. So watch what happens to the gauge when I put it in the cold stuff. Right now it's registering about 15 pounds per square inch. Watch what's happening to the pressure. So this is cold stuff. Is there a relationship between pressure and temperature? Oh wow, I need to heat this back up. Watch it now when I heat it back up. What's happening to the pressure now? Is it going back up? Okay. So is this a direct proportion or is it an inverse proportion? 3, 2, 1. All right, much better this time. This is a direct proportion. That's because as the temperature went down, the pressure went down. When the temperature, temperature went up, then the pressure went up as well. And they're related through a direct proportion. And so what we say then is that P and T are directly proportional. Of course, we had to make an assumption here, and this is that we are assuming that there's a constant volume. This is known by many in the sciences as Gay-Lussac's law, and that's a hyphenated name. And if we want to write a direct proportion now, if we put P1 here, where is T1 going to go? Is it going to go here or is it going to go below?
Right next to it. It's going to get multiplied.
Well, this is a direct proportion. So if we want to model it on the one above, we would have P1 over T1 is equal to P2 over T2. And so if you want to think of it this way, this direct proportion, let's just say that this is 1 and 2, this is 1 and 2, and this is 2 here, then this value must be 4. Because 1 over 2 is equal to 2 over 4. So if we double one, the other one doubles as well. Now, if this was a more advanced mathematics class, we would show the derivations of all of these. Since we're not working with derivations in here, I'm going to show this a different way. I'm going to rewrite the 3 equations that we have like this. And notice now, as we write these out, in all cases, we are showing the pressure up in the numerator, we're showing the temperature in the denominator, and we're showing the volume in the numerator all the way across. And so what we can do is we can combine all of these into a single equation that looks like this. Again, if this is mathematics or a more advanced chemistry class, we'd derive this. We'd say P1 times V1 over T1 is equal to P2 times V2 over T2. And just like we've combined them, this happens to be called the combined gas law. And of all the equations that we're going to be using here in chapter 11, this is the one that's going to be the most important. We do need to remember that our temperatures must be in which units? They must be in kelvins. So again, temperatures must be in units of kelvins in order for us to work with this. Now in fact, when you write the combined gas law like this, you can actually derive all of the other equations very simply. If T1 is equal to T2, they're going to wind up canceling each other out, and you're left with P1V1 is equal to P2V2. If we have pressures constant, we cover those up, and we get Charles' law right in the middle there. And then if volume is constant, V1 is equal to V2, we cover those up, and we get P1 over T1 is equal to P2 over T2, which is the Lou-Sachs law on the end. So if you know the combined gas law or work with it, you can derive all of the other gas laws that we'll be using.